now. So, good day to our thesis advisor, Ma'am Tayactac, and panelists, Sir Honra, Sir Umali, and Ma'am Valdez. We are the thesis group consisting of Jacob Parado, Kevin Oy, Nicole Valle, and I. Will be discussing about the design and simulation analysis performance of IceWind Turbine as a supplement to power demands in Villa Canlaon City. So, uh, first, yeah, um, first is I will be discussing about the Sustainable Development Goals, which which first Sustainable Development Goals is a universal call to action for poverty to end and to protect the planet and to ensure everyone will enjoy peace and prosperity. It is relevant to ME students because one of the many fields in mechanical engineering is renewable energy, which in this research, uh, it will wind energy will be the focus. Okay, so next. In line with the study on the vertical axis wind turbine on Villa Canlaon City, we strongly take affordable and clean energy as well as sustainable cities into account. We will take advantage of the fact that our chosen place is a mountainous area, which is perfect for vertical axis wind turbines being applicable for a windy environment and will be suitable for the collection and utilization of wind energy to be converted to electrical energy for the benefit of the city and will in turn reduce utilities cost and making it more affordable to the people. So moving on, for the background of the study, the wind turbine converts wind energy into electrical electricity using the aerodynamic force from its rotor blades. As wind flows across the blade, the air pressure on one side of the blade decreases. The difference in air pressure across the two sides of the blade creates both lift and drag. So in this case, lift and drag are aerodynamic forces depending on the shape and size of the of the wind turbine. The as such, the lift has a greater force than the drag, causing the rotor to spin. So the rotor is connected to the generator to speed the rotation of the turbine up. This translation of aerodynamic force accompanied with the rotation of a generator translates to electricity. So uh, next is the ice wind turbine itself. It has the following features. First feature is that it has Savonius blade design and it is omnidirectional. It is long term for about 20 years average lifespan and it can withstand extreme weather conditions. It can harvest energy even in low wind speed, even in low wind. It is accessible for both on and off grid systems, and it is advantageous on places such as hilltops, coastal areas, and open plains. So, for the statement of the problem, Villa is a barangay in Canlaon City, a province of Negros Oriental where broad brownout has impacted in the region. Philippine News Agency reported that in a span of a week, Negros Oriental has been experiencing power outage issues that has already occurred 3 times, according to the National Grid Corporation of the Philippines or NGCP. Last October 5, Negros and Panay Islands had unannounced large brownouts where the NGCP reported that electricity units in Negros Oriental had tripped, according to Part Law 2021. The principal source of electricity comes from the power plants in the town. However, due to the recently tripped plant, there has been an increase in demand for power in the area. So, for the research gap, we have first we have application of the vertical axis wind turbine design in the Philippines, which in this case, the research will be focused on IceWind design, which has an Savonius blade design. So next, research gap. According to the previous studies, uh, it is recommended that blade radius ratio R1 should be smaller. So for the general objectives of the study, the main objective is to design and analyze an ice wind turbine and the efficacy of each of the three designs with varying radii through simulation that will reduce the power deficiency that is currently occurring in Villa Canlaon City. So next, for the specific objectives, the first thing is the first part is to research and review related literature regarding ice wind turbine and its designs and efficacy. Next is to design an ice wind turbine through the use of Fusion 360 to create its 3D model. Next is to define the parameters and then conduct the simulation with the use of ANSYS Fluent. And finally, to analyze the effects of varying radii on the efficiency of the ice wind turbine. So moving on, we have the significance of the study. So first is that we are to produce renewable energy. Next is to determine if this type of wind turbine is a feasible and applicable design for Villa Canlaon City. And then our one of the other significance is that we are to reduce the energy shortage in Villa Canlaon City, and then finally to help future researchers in conducting a similar study. So, uh, last but not the least, we have scopes and limitations. For the first limitation is that our location will be limited to Villa Iwa within the city of Canlaon. For the design, we have three varying sizes with three blades for each ice wind turbine design. And for the blade material, we will be using aluminum grade 1100. And for the shaft material, we will be using aluminum grade SUS 304. And for the environment, it is restricted to simulating through a wind tunnel. Therefore, it is only limited wind direction and wind speed. So for the next slide, we will be having Kevin Oy, who will be discussing about the RRL matrices. So there you go.
The RL matrix shows the different RLs created recently for the past 10 years that were gathered and shows the relevance to the study. First is a study entitled A Review on the Performance of Savonius Wind Turbine. Second is the experimental studies of an ice wind turbine. Third is the evaluation of the effects of using different blade material in the performance of an ice wind turbine. And fourth is the performance assessment of a small-scale vertical axis single-stage Savonius wind turbine by using artificial wind. These studies discuss the types of wind turbines such as the Savonius and IceWind. The relevance of these studies to the research is that they allow the researchers to have an idea of what type of wind turbine will be used, the design, and their performance. The slide shows the studies entitled The Effect of the Number of Blades on Wind Turbine Wake a comparison between 2 and 3 bladed rotors, effect of the number of blades and solidity on the performance of a vertical axis wind turbine, the effect of the number of blades on the efficiency of a wind turbine, and the influence of the lengths of turbine blades on the power produced by miniature wind turbines that operate in non-uniform flow fields. These studies discuss the lengths and effects of the number of blades on the IceWind turbine. The relevance of these studies to the research is that they allow the researchers to have an idea of the design, performance, effects, and analysis towards the number of blades in the IceWind turbine. Additionally, the slide shows the studies entitled Materials for Small Wind Turbine Blades, a, a strategic study on the environmental inputs of wind turbine blade materials, their improvements, economics, and end-life operations. We also have experimental investigations of aluminum as a design material for straight-bladed vertical axis wind turbine, and implementation of multi-criteria decision method for selection of suitable material for development of horizontal axis wind turbine blade for sustainable energy generation. These studies discuss all the different materials used in ice wind or wind turbines rather. The relevance of these studies to the research is that they allow the researchers to have an idea of the best material that will be used for the ice wind turbine. Lastly, the slide shows the studies entitled Two-Dimensional Study of Blade Profiles for a Savonius Wind Turbine, Investigation on the Performance of a Portable Power Generation System with a Low-Cost Vertical Axis Wind Turbine, and CFD simulation of a vertical axis wind turbine operating at a moderate tip speed ratio, guidelines for a minimum domain size and azimuthal increment. These studies discuss simulation using different software for the different wind turbines. The relevance of these studies to the research is that they allow the researchers to have a knowledge of what simulator or application will be used to obtain the different results for the study. For the next slide, it will be discussed by Nicole Valle.
For the theoretical consideration, first is aerodynamics, which is the study of how air or gas moves around the moving object. Wind turbines are mostly used to produce electricity from the wind. As a result, aerodynamics is a critical feature of wind turbines. All turbines may be classified as either lift-based or drag-based. The most prevalent drag-type wind turbine is Savonius. Next is the aluminum. Aluminum grade 1100 with a thickness of 1 millimeters will be used for the blades as the type of material aluminum grade SUS 304 for each of the turbine shafts. The researchers have decided to choose aluminum as a type of material for the IceWind vertical axe wind turbine due to its excellent mechanical properties. Aluminum is a type of material which is lightweight, has wear and corrosion resistivity, is an absorbent to moisture, minimum deformation properties, good strength, and high durability. So next is the number of blades. Due to the capacity to harvest energy from the wind, a wind turbine blade is a crucial component of a renewable energy system. The number and configuration of the blades are especially important since they influence turbine speed and efficiency. To optimize total performance and efficiency, the right number of blades must be used to suit the generator performance curve. Next is the tip speed ratio. The tip speed ratio is the ratio between the tangential speed of a blade's tip and the actual wind speed. The effectiveness of a blade is linked to its tip speed ratio, which varies depending on the blade design. Because of the bigger centrifugal forces, higher tip speeds produces more noise and needs stronger blades. The tip speed ratio can be computed by the equation as shown in the screen. Next is the blade arc angle. Blade arc angle is one of the parameters that is considered in the design and efficiency of the IceWind turbine. It is the geometric parameter that represents the angular curvature of the cross-section of the blade. The size of the created vertices created by advancing and retracting blades shows an effect on coefficient, static torque, and rotational speed, wherein the bigger the size of the vertices, the smaller the coefficient of static torque and rotational speed. So next is the blade swept area, which is referred to as the area of the circles generated by the blades as they sweep through the air. The blade swept area can be computed by the equation as shown in the screen. Next is the end plate. The end plate is one of the simple accessories that can be added to the design of the turbine to increase its efficiency. According to AFIFI 2019, distance of end plates increases the average power coefficient and increases the inertia of the rotor, and adding end plates to the design gives a better static coefficient and gives the IceWind turbine a better aerodynamic force. The diameter of the end plates can be computed from the equation as shown. Next is the aspect ratio. The aspect ratio is the ratio between the blade length and the radius of the rotor. It is a decisive parameter in having a satisfactory performance for the turbine, and this has a similar effect as having an end plate to the design. The aspect ratio between 1 and 2 shows a satisfactory performance for the turbine. In the performance of the turbine, the blade arc angle, number of blades, blade swept area, the existence of end plates, aspect ratio, and tip speed ratio were considered to solve for the static coefficient. Next is the power coefficient, which describes how efficiently the turbine converts wind energy to electricity. This can be calculated by the following equation. Next is the Betz limit, which is a limit on the amount of yearly energy that may be harvested at a certain location. Even if a hypothetical wind blew continuously for a year, the energy contained in that year's wind only be taken up to the Betz limit. The Betz law states that when an air flows through a certain region and wind speed reduces due to energy loss due to the turbine extraction, the airflow must disperse over a larger area. Therefore, any turbine's efficiency is limited to a maximum of 59.3% due to geometry. Next is the mechanical power. Mechanical power is generated from the conversion of the kinetic energy of the wind turbine. This is also the power output and is referred to as the rate at which the work can be done. So the mechanical power of the wind can be computed with the use of the following equation. So the next slide will be discussed by Jacob Parado.
For the methodology, presented here is the flowchart of the study. There are a total of 4 phases. Phase 1 is the gathering of data, which is specifically the statement of the problem, information regarding IceWind turbines, and the wind speed of the chosen area, which is Canlaon City. The second phase is the designing of wind turbine using Fusion 360, a 3D modeling software. The third phase is the simulation of the wind turbine using ANSYS Fluent, as it is capable of computational fluid dynamics. Lastly, phase 4 is the analysis of results. Through the simulation, the efficiency of each design will be seen and conclusions will be made. For the methodology matrix, phase 1, which is the gathering of data, online articles were used to identify the statement of the problem, which is the energy deficiency and wind capacity in Villa, Canlaon City. Research and review of related literatures regarding IceWind turbine, its design, and efficacy were performed using online journals and published research from various sources, such as Science Direct, IEEE Explore, and Google Scholar, among others. The designing of the wind turbine was formed by basing it on previous research and modifying it to fit the study. A 3D model for each of the 3 designs will then be made using Fusion 360. Phase 3 is a simulation of the wind turbine. Parameters will be first defined, especially for the wind tunnel that will be simulated using ANSYS Fluent. A wind tunnel will be simulated as the data that was only available is the wind speed within the chosen area. Following that, the created 3D model will then be imported to ANSYS Fluent, where the performance of each wind turbine will be simulated within the wind tunnel. Lastly, the analysis of the performance of the wind turbine in relation to its varying radii will then be performed and conclusions will be drawn thereafter. For the appendices, Appendix A is a proposed budget plan. However, since the researchers will only be using their personal computers and the free simulation software, no new additional costs will be made. The following are the specifications of each of the computers that each member has. And lastly, Appendix B is the Gantt chart, which shows the schedule that this study followed while performing the current course. That is all. Thank you.